Hello everyone, I'm Kieran Gopinathan, and today I'm going to be presenting GopCamel, a structural editor for OCaml. Now before we begin, let me ask you a little question. Have you ever struggled with your editor to express complex transformations of OCaml source code in terms of simple, low-level lexical operations? Have you ever sought to search through a large and complex OCaml codebase using fairly dumb, regular expressions to struggle to find your way around? Well, if you answered yes to any of those questions, then GopCaml is the plugin for you. The structural editing capabilities provided by GopCaml will literally allow you to edit at the speed of thought itself. But fair warning before we proceed, the structural editing capabilities provided by GopCaml may change the way you write code forever. And it is addicting. So be prepared for the consequences. Okay, with the elevator pitch aside, let's get down to business and see how exactly this thing works. Okay, so let's say that you're writing a function in OCaml, as one is oft to do. Now, over the course of the implementation, for any one of a number of reasons, you may find yourself in a situation where you need to change the definition of the function that you're writing. For example, maybe you want to add another argument, maybe the name of the function is no longer accurate, maybe you want to explicitly annotate the types of the arguments, or as the case here, maybe you want to make the function recursive. The key point that I'm trying to make here is that this is a fairly common operation that is somewhat non-trivial, so it would be nice to have some kind of editor support for this operation. But how exactly should we provide editor support for this operation? Well, we can take some inspiration from Emacs. It turns out that Emacs actually already has a binding for this operation. In particular, pressing Ctrl-Meta-A runs the function beginning of define. And so when you're editing Emacs Lisp code, this will move your cursor from its current position to the start of the nearest enclosing function definition. So, turns out the editor is already configured. The only problem is that this is only defined for Emacs Lisp. So we need to provide a definition for OCaml. But how exactly should we implement this? Well, as a first attempt, we might say that every let binding begins with a let. So can't we just search backwards for the first preceding let? Well, this kind of works, but what about let expressions? That kind of throws a wrench in things. But wait, it gets even worse. What about local modules? Because these modules could have let bindings within them. The key point that I'm trying to make here is that it's not quite as simple as it might seem. And this is fundamentally because OCaml doesn't really have any kind of required lexical tokens needed to denote the start and end of expressions. And so it makes it very hard to determine these kind of structural operations using the kinds of lexical operations that an editor framework might provide. And actually, if we zoom out a bit, it turns out that we're actually brushing up against a sort of fundamental dichotomy in the design space of programming languages. So now, if I were to plot out the programming languages on this little graph here, where on the x-axis, as we move to the right, we reduce the level of syntactic redundancy in our language. Then we can plot languages like Lisp on the far left, because they have very high amounts of syntactic redundancy. In particular, every expression is denoted by an opening and closing parentheses. Conversely, we can plot ML family languages on the far right, because they have very little syntactic redundancy, as we thought about earlier. And in the middle, we can place languages that are C or C-like or like Rescript. Now, it turns out that this notion of syntactic redundancy is a sort of double-edged sword, because by having a lot of syntactic redundancy, languages like Lisp can easily provide robust editor support, because it's very easy to work out where expressions should be. But the problem with this is that it makes programs written in the language very noisy. It's very hard to parse Lisp program as a human, unless you're used to dealing with these kind of parentheses. Conversely, with ML family languages, by their virtue of very little syntactic redundancy, they have a very clean and concise syntax that makes them a pleasure to read and write. But this comes at the cost of having very ad hoc editor support. So this is kind of the fundamental dichotomy that we're brushing up here. But is it possible to do better? Is it possible to get the best of both worlds? Well, what if we were to track the syntax tree from the editor? This way we could bypass this dichotomy and get a very syntactically clean language while also getting very high quality editors for. And this is exactly the insight that inspired GopCaml mode. So, to summarize, GopCaml is an editor-agnostic generic framework for structural editing of OCaml code. Now, to do this, it leverages the OCaml compiler pipeline for faithful parsing of OCaml code. And then on top of this, it provides functionalities to track and maintain the concrete syntax tree for an edited file. And on top of this, defines common editing operations as AST transformations, thereby allowing for a fundamentally different way of editing OCaml code. Now, GopCaml mode is a particular Emacs plugin that uses the GopCaml framework to provide robust and consistent editing support for OCaml code in Emacs. And the beauty of this implementation is that it seamlessly integrates with existing Emacs workflows. When you need the structural editing capabilities of GopCaml mode, the functionalities are merely a keybind away. And when you don't, the plugin simply fades into the background, and you wouldn't even know that you had it installed. So hopefully that's piqued your interest, and in the rest of this talk, I'll give you an overview of this work. So we're going to start off by going through a little tour of the various features of GopCaml, and then we'll do a little bit of live coding to see how it all fits together. And then we'll talk about how exactly it works and the implementation of the framework itself. And finally, I'll talk a little bit about the future work and where I hope to take it from here onwards. So, without further ado, let's get started. Perfect. So let's begin with a quick whistle-stop tour of the key functionalities provided by GopCaml. In particular, the 5 functionalities that you can see on screen. Move to definition, structural navigation, structural transposition, structural deletion, and extract expression. Now, there are a couple of other quality of life functionalities that GopCaml mode also provides, but for the purposes of this video, we won't be covering them. So the first functionality we'll be looking at, as hinted by the introduction, will be the move to definition operation. So the idea here is that when the user presses the key binding Control Meta A, the editor moves the cursor from its current position to the start of the nearest enclosing function definition, as you can see on screen. Now, because this functionality is so robust, it works perfectly fine, even when you're dealing with really large expressions with several let bindings in between them, and even when you're dealing with local modules that may have bindings within them themselves. Now, while we're starting off with a fairly simple functionality, this turns out to be particularly useful, especially when you're dealing with really large function definitions that don't even fit on screen. In this case, trying to do a manual approach would likely be very disorientating, so this is actually pretty nice. Now, the next functionality is structural navigation, which allows a user to navigate through code in terms of the syntax tree. And this is where it starts getting interesting. So as I mentioned before, OCaml has very little syntactic redundancy. So there aren't clear lexical markers to denote syntactic constructs. So how do we convey to the user their position in the syntax tree? Well, to do this, we introduce an entirely new modality. When the user presses a key binding for structural navigation, as shown on screen, the user enters the zipper mode. We'll look into the reason why it's called that in a bit. And in this mode, the editor tracks the structural position of the user and highlights it as a small overlay, as you can see on screen. So with these key bindings, the user can freely navigate through the AST. And it turns out to be very useful, especially when you're dealing with very large match statements where one branch may span several pages. So very nice again. And now that we have this zipper-based interaction scheme, it turns out that we can actually tack on several other useful functionalities on top. And structural transposition, the next functionality, is one such addition. So the idea here is that whenever you run one of the structural navigation key bindings and add a shift to it, it becomes a structural transposition or structural movement operation. And rather than just moving the cursor, the editor moves the entire selected syntactic construct through the syntax tree, as you can see on screen. So as it turns out, one useful place where this is particularly nice is when editing module signatures, where it's actually very useful to be able to just freely move around various declarations without having to worry about very syntactic issues. And a nicety is that it also carries around the comments as well, so pretty good. The next extension that branches off zipper mode is structural deletion. So the idea here is that when the user presses the key binding to delete either Control Meta D or Control Meta W, the editor removes the selected syntactic construct from the syntax tree, and this makes it very easy to refactor codebases. Again, another place where this turns out to be useful is in editing module signatures, where you can freely remove various declarations by just pressing one key binding. And the final functionality that we're going to be looking at is extract expression. Now, this isn't strictly based on zipper mode per se, but more to highlight the kind of additional functionalities that you can support if your editor has a deeper understanding of the syntax. So when the user presses the key binding Control-C, Control-E, the editor attempts to extract every instance of the selected expression into the nearest enclosing let binding. So unlike tools like Rotor, this isn't guaranteed to be sound and may entirely change the semantics of the program, especially if you're dealing with references, etc. Now, it is partially aware of scope and will try and extract the expression to the nearest enclosing scope that contains all the variables in the selected expression, but it can't really make any guarantees. And this is perfectly fine because it's not intended to be a large-scale refactoring tool, but rather a lightweight, quick operation that a user can use in anger while editing. So that kind of covers the main kinds of functionalities that I want to cover in this video. But so far, I've only shown you these different features in isolation. To get the full experience of GopCaml, we'll need to see how these functionalities all happen to interact during actual coding. So talk is cheap, let's do some live coding. So, as they say, the proof is in the pudding. So today we're going to do a little bit of live coding for you. We're going to be writing a simple evaluator for a small term-based language. And this language is adapted from types and programming languages. So as you can see, it's fairly standard. We have constructors for true, false, if statements, zero, suck, and is zero. Pretty basic. Let's write an evaluation function for this then. So we'll start with let eval t equals t. Now I'd like to destruct on this t term, but unfortunately because it's an abstract type, Merlin doesn't allow me to do that. So we can press Control-C, Control-P to take us to the nearest parameter, and then we can explicitly annotate the type as being term. And then if we move back, Merlin will allow us to do the destruct again. Now once we've destructed, we can have a look at the cases here. And we can see that actually when we're implementing an evaluator, there are only two particular cases that we care about. That is tm if and tm is 0. Now, moving these all to the top, we can then delete the rest and just replace them with a raise no rule applies exception. Okay, now moving back to the remaining cases, what we can do is we want to duplicate a couple of these. So the if statement should be duplicated at least 3 times, and the 0 statement should be duplicated twice. So let's implement the tmif. The reason for the duplication is that if we're dealing with a tmif of a tm true term, then we can simply evaluate this by returning the if branch. And if we're dealing with a tm false, and the conditional is false, then we can just simply return the else branch. So that's pretty simple. Now let's move on to implement the full case, where we need to evaluate the condition. So we can name each one of the parameters, and let's start evaluating the conditional first. But wait a minute. In order to evaluate this, we need to make the function recursive, but we haven't made it recursive. Now we can use move to definition to quickly jump to the definition, add a recursive annotation, and jump straight back. And now we can call eval without any problems. Let's eval the remaining terms, so eval t2 and eval t3. And once we've done this, we just need to return the exact term that we started off with, Just to simplify things, I'm going to just copy the thing that we matched on and paste that exactly as the return statement. Now let's handle the 0 is 0 cases. So where tm is 0 of it is 0, then we just return tm true. And if we're dealing with a tm is 0 of an unevaluated term, then we just need to eval it as we did before, and then return tm is 0 of this newly evaluated term. So pretty simple, pretty straightforward, pretty cool. Alright, so now that we've had a chance to see GopCaml mode in action, now let's take a look under the hood to find out how exactly it's implemented. So, how exactly is it implemented? Well, I told you earlier that it's implemented by tracking the concrete syntax tree for the currently edited file. But it turns out it's not quite that simple. And this is because of one small problem. And to understand what that problem is, let's take a look at the OCaml syntax tree. So I've thrown on screen a snippet from the definition of the OCaml syntax tree, the part that defines an expression. And as we can see, it's fairly standard. One can easily imagine how you can instantiate this data type to construct various trees to represent the types of programs that users might throw at you. But there's one small problem with this definition, and that is that this definition is inherently static. It's not suited for an interactive traversal, the kind of traversal that we would have to do if we're trying to implement structural transformations. So how do we solve this problem? Well, it turns out that this problem, that of performing an interactive traversal of a data structure like a tree, is a fairly standard operation. And it turns out it has a fairly standard solution. That is, a zipper. So the zipper data type, originally conceived by Hewitt, is a functional data type that represents an iterator over a data structure like a tree. Now, in our case, we've made a few small modifications to make a zipper that's tailored for editing. Now, to understand what this definition means, you have to understand that a zipper represents a path through a tree. And so at every instance, the zipper will be focused on one particular element of the tree. Now, with this context in mind, we can understand each one of the fields as follows. The parent field represents the immediate parent of the currently focused element. The sibling fields, the above and below, represent these siblings that are immediately preceding the current element, or the ones that precede. In this case, there are none. Now, the main modification that we've made is to add this additional field, bounds, that represents the text region that encompasses the entirety of the currently selected element and all of its children. And this turns out to be really useful for editing, because it means that we don't need to understand the contents of a node in order to perform transformations on it. We can simply tell the editor to move or remove the text region that corresponds to the entirety of the selected syntactic construct. Now, the zipper also has this constructor top that represents a path to the root of the entire syntax tree, and we also represent the currently selected item using this item field. Now, this item field has a type of t, but this t is not just an alias for the OCaml syntax tree, it's actually a fancy wrapper. And this allows us to implement this kind of lazy zipper for editing. The idea here is that rather than converting the entire OCaml syntax tree into our zipper format, we gradually convert the syntax tree by wrapping it initially in this data type, and then as the user moves through the tree, we convert these instances into this generic data type that loses all the additional extraneous information and only tracks the bare minimum structural information needed to perform these kinds of operations. So hopefully that gives you an idea of how this is implemented. But how exactly do we use this zipper to implement structural transformations? Well, to get an understanding of the intuition behind how this works, let's take a look at a few of the structural transformations that we've seen previously. Let's start with structural navigation. Now, as it just so happens, this concept of a focus node in the zipper maps one-to-one with this notion of a focused syntactic construct in our so-called zipper mode. And so in order to implement transformations, in order to implement movements, we can simply update the zipper. So for example, in order to move up, we would select the parent using the parent field and then update the zipper accordingly. In order to descend into a node, we would need to break into it and convert it into a generic format, select the first child, and then update the zipper to point to the first child. Similarly, if we wanted to move to any of the siblings, we could select the above or below fields and update the zipper accordingly. So fairly concise and an elegant implementation of this operation. Now, the second operation is structural transposition, and this is slightly more complex, although still fairly simple. In order to implement transposition, we first have the zipper that's focused on one particular element, then we work out the element that we're going to be swapping it with by looking at either the sibling above or below fields, and once we've found this other element, we can then implement the transposition by extracting the text regions that correspond to both of these selected elements, and then asking the editor to implement this swap of these two text regions. And once that's done, we can update the zipper and update the corresponding text regions, and the zipper is now up to date. So once again, fairly concise. The final operation that we're going to look at is structural deletion. Now, deletion is slightly more complex, although still fairly nice. Now, the way we implement deletion is the zipper will be focused on a particular element. Now, when we want to delete it, we need to work out where the zipper should move to. So we select either the parent or the sibling, in this case there's a sibling, and update the zipper accordingly. Next, we just simply remove the deleted element from the syntax tree and ask the editor to remove the text region corresponding to that deleted element. But we're not quite done yet, and that is because the text region has been removed. This means that all text regions for the ancestors of the current node are now invalidated. So we need to ask all ancestors to update their text regions to account for this removal. And then we also need to ask every sibling of the ancestor to adjust their text regions to be shifted backwards according to this deleted region. And once we've done that, the deletion has now been implemented. So hopefully that should give you an intuition as to how we implement structural operations using a zipper. But there's one part of this implementation that I've been particularly vague about. And that is, how do we integrate this with an editor? Well, to understand this, let's take a look at the system architecture for the overall tool. Now, currently we've only had support for Emacs, but it turns out, as we'll see, this is not a large limitation. So our architecture begins with this instance of the Emacs editor, which has a buffer that contains the code that the user is editing. Now, on top of this, we provide a package, gopcaml mode, that is actually written in OCaml using JaneSpeed's eCaml library to allow us to dynamically bind to the Emacs instance. Now, with this package set up, in order to build the AST, we then, because we're writing in OCaml, we can just reuse the OCaml parser to get 100% faithful parsing of the user's code. And once we've done this, we can then convert the AST into the zipper using the operations that we've seen previously. And with this, the package is set up. Now, whenever the user submits any kind of transformation or structural operation, we work out how to implement that operation in terms of the zipper. And once we work that out, we then tell the editor to enact that change in terms of fairly simple text operations. And this means that the editor is actually 100% unaware of the complexity of dealing with OCaml syntax. And a nice consequence of this is that it means actually the architecture is fairly generic over the choice of editor. And so in theory, in the future, we could actually modify it to support other architectures. So that kind of wraps up everything that I wanted to speak about today. Just to summarize the main points, gopcaml is an editor-agnostic generic framework for structural editing, and to implement this, we leverage the OCaml compiler pipeline for faithful parsing and use a mix of zippers and ASTs to implement these kinds of structural transformations. gopcaml mode happens to be a particular Emacs plugin that uses the gopcaml framework to provide robust and consistent OCaml support for Emacs. Now, in the remaining few minutes of this presentation, I just want to take a second to talk about potential directions that I hope to extend this project in the near future. Now, the first such direction is, as I mentioned, support for other editors. Another direction that would be nice is to have robustness to invalid syntax. Currently, the buffer has to be syntactically valid in order for the structural operations to work. But it would be nice to have support for invalid syntax, a la Merlin. Ideally, I'd like to reuse the Merlin compiler, but unfortunately, it's not really exposed in a way that is easy to reuse. Another direction would be to have additional semantic-aware transformations. Currently, we only do very basic structural syntactic analysis for our extract expression, but seeing as we're tracking the entire AST, it seems like there's lots of potential for doing some more semantically aware transformations. For example, maybe an extract expression that is in fact sound and guaranteed not to change the behavior, a la Rotor. And a final direction that would be nice is support for meta-OCaml programs. Currently, the syntax of meta-OCaml isn't supported by the current parsers that we support, and so we can't really do structural editing of meta-OCaml programs. So that's about everything that I had to say. Hopefully I've managed to pique your interest, and if you are interested, I'm pleased to tell you that gopcaml mode is actually currently available, and it's a breeze to install. Just simply download it from OPAM, and then load it in your Emacs.d. As a warning, you will need an Emacs instance that supports dynamic modules. Now, if you're interested in contributing or looking at the code, feel free to check out the QR code in the corner or the link above it. And I guess that's about it. So thank you for your attention, and I look forward to your questions.